Today we will introduce another key reason that physicists need to build larger, more powerful, more intense particle colliders, an energy distribution that we currently know very little about, but which shaped the very earliest moments of our universe and which may control its ultimate violent fate. Today we will discuss the Higgs potential. There are those that claim that particle physics is in crisis, people who claim that the field has stagnated, communicators who insist that building larger, more powerful, more expensive colliders is a waste of time, effort, and money. Nothing could be further from the truth. The discovery of the Higgs boson in 2012 is often pitched as the end of a journey, the discovery of the final missing puzzle piece of the Standard Model. In reality, that discovery was the very first step in an ongoing and vital program of experimental study. The Higgs boson is the first ever seemingly fundamental spinless scalar particle that we have ever observed. It sits at the center of the Standard Model, linking it all together. It is a unique probe of the fundamental constituents of our universe, its history, and its future. There is still so much about the Higgs boson and Higgs field that we do not understand. So many deep questions that need to be answered. So many riddles of our universe that can only be unraveled by exquisitely understanding the Higgs. One aspect of the Higgs sector that physicists are desperate to understand is the form of the Higgs potential, the Higgs field's contribution to the energy density of the universe's vacuum, the energy density of free space. The shape of that potential may be the key to understanding why matter predominates over antimatter in our universe, meaning that the Higgs is at the very heart of why we even exist. The nature of the Higgs potential may also control the ultimate fate of our universe by allowing it to collapse to a lower energy vacuum in a violent flash, meaning that the Higgs is at the very center of where our universe may be heading. And the form of this potential may reveal where new physics and a new layer of nature beyond the Standard Model is hiding, meaning that the Higgs is at the very forefront of efforts to peel back the next layer of the microscopic world. The Higgs potential is the key to unlocking answers to existential questions that humans have wrestled with for thousands of years. Why are we here? What are we made of? And where are we going? The currently active Large Hadron Collider is attempting to narrow the parameters of the Higgs potential, but it can only take us so far. To continue to seek some of the most consequential answers to some of the most far-reaching questions, we need larger, more powerful, more intense particle colliders. Explaining the importance of the Higgs potential is a doorway to telling some of the most exciting, intriguing, and potentially important stories in fundamental physics. In this two-part mini-series, we will read some of them together. In this video, I will explain what the Higgs potential is, the problems it addresses in high-energy particle physics, and why we still know very little about its form and evolution. In part 2, we will explore why mapping the form of the Higgs potential is so incredibly important, how that mapping can be done, and the absolute necessity of building new, more powerful, more intense particle colliders to perform that mapping. So let's get started. What is the Higgs potential? The Higgs potential is the Higgs field's vacuum energy density, the energy density stored in the Higgs field, the energy density of empty space. This potential energy distribution is a function of the strength of the Higgs field in the vacuum of our universe, and in the Standard Model, takes a well-defined form. The scalar Higgs field itself is a black swan amongst quantum fields. Quantum field theory tells us that the vacuum of our universe isn't really empty, but in reality is a boiling sea of quantum fields associated with every fundamental particle we know and do not yet know. Usually, the potential energy of these fields takes a parabolic shape, and these fields, although oscillating, take an average value of 0, the value of the field that minimizes the potential energy overall. We can excite fundamental particles out of these fields by pumping energy into them, like we do at particle colliders, but on average, they are turned off. However, in the modern universe, the scalar Higgs field seems to be an omnipresent treacle, permeating the universe and imbuing fundamental fermions with mass. Evidently, the current vacuum of our universe has the scalar Higgs field dialed up to a non-zero vacuum expectation value everywhere. How can this be the case? How can having a field constantly cranked up create a minimum in the energy density of the vacuum overall? The standard model insists that this reality is the result of a phase transition in the very vacuum of our universe in its earliest moments, the Electroweak phase transition. During that phase transition, the vacuum of our universe rolled down the Higgs potential energy hill into its current state. The W and Z bosons acquired their mass, and the scalar Higgs field was powered up, so that fundamental fermions can ping off it and acquire mass of their own. The form of the Higgs potential solves a multitude of problems in particle physics, and in the standard model, that form is set in stone. To better understand the form and importance of the Higgs potential in that phase transition, it will first be instructive to consider the Landau theory of phase transitions, and a simple phase transition and potential in a toy system, a ferromagnet. Landau theory has proved to be incredibly successful in describing a broad range of phase transitions, including the Landau-Ginzburg theory of superconductivity. Consider a simple 2D system of atoms arranged in a plane. Each atom has a magnetic moment that can point either up or down. At high temperatures, above the phase transition or critical temperature, the atoms flip between pointing up or pointing down due to their thermal motion. The system is disordered, but on average, there are an equal number of magnetic moments pointing up and down, and the system has zero net magnetization. However, when the system is cooled below the critical temperature, the atoms align magnetic moments to minimize the overall potential energy of the system. The system becomes more ordered and develops a net magnetization in a particular direction, up or down. The magnetization is the order parameter of the system. It increases from 0 to a finite value. Notice that the system can produce a net magnetization in either the up or down directions with equal probability, as both choices align the magnetic moments and lower the potential energy of the system by the same amount. We say that the potential energy of the system is symmetric with respect to up to down rotations. In Landau theory, the potential energy of the system in the vicinity of the critical temperature is given by the following equation: alpha magnetization squared plus beta magnetization to the power 4. Notice that only even powers of m are permitted, as otherwise the potential energy of the system would be dependent on whether the magnetization pointed in the positive up or negative down direction. In theory, higher order terms in magnetization to the 6 or magnetization to the 8 are also permitted. The beta coefficient in the potential energy equation is always positive. However, the alpha coefficient switches its sign depending on the temperature. Above the critical temperature, alpha is positive, and the potential shows a single minimum at 0 magnetization, where the system sits above the critical temperature. Alpha decreases as we approach the critical temperature, and at the critical temperature it becomes 0, and the potential has a wide flat bottom, still centered around 0 magnetization. However, below the critical temperature, alpha flips sign and becomes negative, and the system develops two identical deep minima, one corresponding to all magnetic moments pointing up, and the other corresponding to them pointing down. We can find the position of the minima with simple differentiation, plus or minus the square root of minus alpha over 2 beta. Below the critical temperature, the system spontaneously falls into one of these two minima. Switching on a directional magnetization now leads to the system sitting lower in energy than not doing so, and maintaining an overall magnetization of 0. Notice that there is an important difference in symmetry between the high temperature and low temperature phases. In the high temperature phase, the potential energy of the system and the magnetization of the system, on average 0, were symmetric with respect to up to down rotations of the magnetic moments, and hence swapping m to minus m. 0 equals 0. However, in the low temperature phase, below the critical temperature, the rotational symmetry of the magnetization has been lost. Swapping the magnetic moments from up to down changes the physical sign of the magnetization. But, crucially, the potential energy of the system has remained symmetric and invariant under such rotations. Notice that the loss of symmetry in the final state is accompanied by a gain in order of the system, as measured by the order parameter, the overall magnetization of the system. This kind of symmetry breaking, where the energy given by the underlying interactions is symmetric, but the states of minimum energy are not, is known as spontaneous symmetry breaking. The underlying physics between magnetic moments is completely symmetric and ambivalent with respect to up to down rotations, but that fact is hidden by the observation that all the magnetic moments are pointing up or pointing down after the phase transition to the low temperature phase occurs. When we only observe the final state of the low temperature phase, we are tricked into believing that the underlying physics of magnetic moments is not symmetric with respect to up to down rotations, that there is some underlying preference for magnetic moments to all point up rather than down. However, that is not the case. The underlying symmetries of the fundamental physics are completely intact. They are just not manifest in the specific final state. Another example of spontaneous symmetry breaking is a ball sitting on the apex of a smooth hill. When it rolls down the hill to a lower energy final state, it could choose to roll down along any path, but it has to choose one. There is no preferred direction dictated by the physics of gravity, but when we observe the ball sitting to the east of the hill, we might believe that gravity favours falling to the east, but it does not. Again, the underlying symmetries of the fundamental physics are completely intact, but they are not manifest in the final state of the system that we observe. Symmetry has been spontaneously broken. The important point to take away from this section is that the underlying physics of a system regularly displays important symmetries, rotational symmetries, reflection symmetries, or, in particle physics, gauge symmetries. In the case of a ferromagnet, the underlying physics of magnetic moments does not favour making magnetic moments all point up or all point down. However, when a system has numerous ground states with the same minimum energy, for example all magnetic moments pointing up or all magnetic moments pointing down, it is energetically favourable for the system to roll into one of those ground states, and it does so spontaneously with equal probability. However, when we later observe the system in a specific ground state, for example with all the magnetic moments pointing up, it can appear that the system has a preference for manifesting that ground state, and that the underlying physics of the system must in fact be not symmetric under up to down rotations. This is not the case. The symmetries in that underlying physics are completely intact. It's just that those symmetries do not apply to the specific ground state configurations of the system, only to the energy of those configurations. We say that the underlying symmetries of the physics have been spontaneously broken. So, we now understand a simple ferromagnetic phase transition, but how does this relate to the electroweak phase transition of the vacuum of our universe? And how does it relate to this Higgs potential? Well, notice how the spontaneous switching on of a non-zero magnetization throughout our toy ferromagnetic system closely mirrors the powering up of the Higgs field to a non-zero vacuum expectation value throughout the entire universe. Perhaps the universe itself underwent a similar phase transition, a phase transition that switched on the scalar Higgs field everywhere in our universe. It turns out that this idea solves a number of deep problems in high-energy particle physics. By the 1960s, quantum field theory had already successfully described the physics of electromagnetic interactions. However, applying quantum field theory to the weak interaction, which controls radioactive decay, was proving impossible due to a fundamental stumbling block: The theory didn't allow for particles to have mass. If the bosons that control weak interactions are not massless, the fundamental underlying gauge symmetries of the theory are broken, and the theory collapses mathematically. Electroweak theory, where the weak force and the electromagnetic force are unified, predicts that 4 massless bosons should control electromagnetic and weak processes. We call them the W1, W2, W3, and B. This posed a major problem in the 1960s, since it was clear that the weak force carriers had to be massive to be consistent with their very short range and the slower pace of weak interactions and radioactive decay that scientists had observed. As such, scientists needed a workaround to explain how it could look like the weak bosons we know today, the massive W+, W-, and Z, appear to break the underlying gauge symmetries of electroweak theory, but in reality, do not. They needed a mechanism that explained how electroweak fields could obey the underlying symmetries of gauge field theories that demanded that all gauge bosons should be massless, but result in a final vacuum state of our universe that does not. The parallels to Landau's theories of phase transitions and its associated spontaneous symmetry breaking were undeniable, and Peter Higgs and his contemporaries sought to introduce Landau's ideas into particle physics in the 1960s. It turned out that the key to solving both the problem of the mass of the W and Z bosons and the non-zero value of the scalar Higgs field throughout the universe is the same. A new field present from the very beginning of our universe, the primordial Higgs field, and Landau's sleight of hand, spontaneous symmetry breaking. What Higgs and other brilliant 1960s theoretical physicists proposed was that just like our simple ferromagnetic system, the very vacuum of our universe had undergone a phase transition in its very first nanoseconds, the electroweak phase transition. This phase transition gave mass to the W and Z bosons and powered up the scalar Higgs field that pervades the universe today, imbuing mass to fundamental fermions. Here's how it works. Peter Higgs hypothesized that the Higgs field existed in the very earliest moments of the universe, but at that point it had 4 components. It was a field that specified 4 values at different points in space, just as we can specify the temperature, humidity, pollen count, and air density at different positions in a room. It had 4 degrees of freedom. For those who are slightly more mathematically minded, these 4 degrees of freedom can be expressed as 2 complex fields with 4 components. Higgs also postulated that the potential energy of this field took the following form: mu squared phi dagger phi plus lambda phi dagger phi squared, where mu squared is the mass squared term and lambda is related to the Higgs self-coupling strength, something we'll discuss in part 2. Notice how the potential energy Higgs gave to this field looks exactly like the potential energy in the Landau theory of the ferromagnet, just with the order parameter of magnetization switched to being the strength of the Higgs field. That is no coincidence. Higgs lifted this potential straight from Landau's work. Notice also that just like the potential energy of the ferromagnetic system was invariant under up to down rotations, the potential associated with the Higgs field is symmetrical to rotations in phi space. Swapping around the phi components leaves the potential energy of the system unchanged. At extremely high temperatures in the very early universe, above a critical temperature, the mass squared term was positive, just as the alpha term in our ferromagnetic system was positive, and all 4 components of the Higgs field had an average value of 0, just as our toy ferromagnetic system had an average magnetization of 0. Notice that when the vacuum was at the origin, with all the Higgs field components taking an average value of 0, rotations of the 4 components of the field did nothing to the physical state of the system, just as swapping up for down did nothing to the magnetization of our ferromagnet. Symmetry was maintained, and there was no constantly turned on Higgs field component for fundamental particles to bounce off and acquire mass. Particles were massless and whizzed around at the speed of light. However, as the universe expanded and cooled, its temperature dropped below a critical value, and the vacuum underwent a phase transition. Just as for the ferromagnet, our mass squared term turned negative. The electroweak phase transition occurred. Just as in the ferromagnetic system, the potential energy continued to be symmetric to rotations in phi space, but a ring of degenerate final state energy minima developed. The position of that ring of minimum energy states can again be found by simply taking a derivative of the potential and setting it equal to 0. The 4 field component squared terms have to sum to minus mu over lambda. This is hard to visualize in 4D space, but it creates a ring of identical lowest energy vacuum ground states in complex space, the famous Higgs wine bottle potential. The early vacuum of our universe, just like the ferromagnet, was now free to roll down the potential hill into any one of these final state minima, and it did so. However, when the vacuum rolled down into this specific minimum, it chose a specific direction. This is just like our ball rolling eastward down the hill, and it spontaneously broke 3 directions of the Higgs field. Observe. If we now rotate the system, we turn on different components of the Higgs field. Rotations change the physical nature of the system, turning on and off different components of the Higgs field. The vacuum ground state of the system is no longer symmetric under rotations of the Higgs field components. Just as in our ferromagnetic system, the magnetization switched between M and minus M as we rotated up into down. The symmetry of the Higgs field has been spontaneously broken. It is not manifest in the final state of our vacuum. So we now have a Higgs field component turned on throughout the entire universe, a field fermions can bash off to acquire their mass. But there's more. There is a famous theory in particle physics known as Goldstone's theorem that states that when a continuous symmetry exists and is spontaneously broken, integer spin particles, bosons, will be generated. These Goldstone bosons are massless and generated in numbers that correspond to the number of degrees of broken symmetry. So in this case, the spontaneous symmetry breaking of 3 directions, or components of the Higgs field, generates 3 massless Goldstone bosons. And here's where the magic happens. These Goldstone bosons have the same quantum numbers as 3 of the 4 massless electroweak gauge bosons that appear from electroweak theory: the W1, W2, W3, and B. That means they can mix together. Notice that the Higgs field had 4 degrees of freedom before spontaneous symmetry breaking, and that massless gauge bosons like the W1, W2, W3, and B have 2 each, just like a massless photon has 2 transverse polarizations. That's a total of 12 degrees of freedom before spontaneous symmetry breaking of the Higgs field. Now, when the electroweak gauge bosons and the Goldstone bosons from the spontaneous symmetry breaking of the Higgs field mix together, the degrees of freedom are repackaged into the force-carrying bosons we know today: the massless photon and the massive weak W+, W-, and Z bosons. After this process, we have the massive W+, W-, and Z bosons we see in our universe, with 3 degrees of freedom each, 2 transverse and 1 longitudinal, the massless photon with 2 degrees of freedom, and 1 degree of freedom left over, a degree of freedom that represents a new scalar particle, the massive Higgs boson, predicted by Peter Higgs himself in 1966. 12 degrees of freedom before the spontaneous symmetry breaking of the Higgs field, 12 degrees of freedom afterwards. By the end of the electroweak phase transition, the W and Z bosons have mass, and at no point were the W1, W2, W3, and B gauge bosons required to have mass and break their underlying gauge symmetries. The spontaneous symmetry breaking of the Higgs field did all the work, imbued them with mass, and just left a final state of the universe where it looks like the gauge symmetry was broken. In reality, As with our ferromagnetic system, or ball rolling down a hill, the underlying symmetries of the fundamental physics are completely intact. They are just not manifest in the final state of the vacuum. This process also left us with an omnipresent scalar Higgs field switched on everywhere in the universe, a field off which fundamental fermions can ping to obtain their mass. Peter Higgs and his contemporaries had applied Landau's theory of phase transitions in ferromagnets to the very vacuum of our entire universe, and in doing so had found a loophole to provide fundamental particles with mass without breaking the symmetries essential to gauge field theory. This was an incredibly beautiful, if diabolically subtle, theoretical breakthrough. Don't worry if you have to listen to this section a couple of times to get a handle on it. The important point to take away from this section is that the form of the Higgs field and Higgs potential was chosen by Higgs in such a way that a phase transition in the very early universe could provide just the right amount of spontaneous symmetry breaking to produce the three massive weak gauge bosons we see today, and to switch on a scalar field throughout the universe that explains how fundamental fermions acquire mass. The forms of the Higgs field and the Higgs potential were chosen to get the jobs done. Putting this Higgs mechanism together with electroweak theory in 1967 was the beginning of the formulation of the modern Standard Model. However, the existence of the Higgs field still had to be determined experimentally, and the predictions of the Higgs mechanism had to hold up. In 2012, the Higgs boson, the excitation of the turned-on scalar component of the Higgs field, predicted by Peter Higgs, was discovered. It appeared that the Higgs field was real. So the Higgs mechanism solves a lot of deep problems in theoretical particle physics, and it seems like the Higgs field exists. So presumably that means that Peter Higgs was entirely justified in lifting the Higgs potential from Landau's work, and that the Higgs potential of our universe is exactly that which he predicted. Well, not so fast. We first need to ask how the predictions of the Standard Model Higgs mechanism line up with experiment. The classical Higgs potential outlined by Higgs and others depends on only two parameters, μ² and lambda. The values of these parameters are not predicted by theory. They are related to the mass of the Higgs boson, the excitation of the scalar Higgs field, and the well-known strength of the Fermi constant from electroweak theory. Notice that theory does not predict the mass of the Higgs boson from first principles. It was discovered by experiment in 2012. This allowed the μ² and lambda parameters to be calculated, and the minimum of the Higgs potential, the vacuum expectation value, or VEV, to be determined. With these values in hand, the Higgs mechanism can predict the mass of the W boson and Z boson, and these predictions prove to be in excellent agreement with experiment. The Higgs mechanism also predicts that fundamental fermions, quarks and leptons, should couple to the Higgs boson with a strength that is proportional to their mass. Measurements of these couplings made over the last decade at the Large Hadron Collider for the heaviest fundamental fermions have been entirely consistent with that prediction. So it seems that the Higgs mechanism works. Surely the Higgs mechanism is the entire answer to how particles acquire their mass. Well, again, not quite so fast. There is a huge prediction of the Standard Model Higgs mechanism that we haven't even come close to verifying: the shape of the classical Higgs potential. It turns out that the mass of the Higgs boson is related to the curvature of the classical Higgs potential around its vacuum expectation value, around its minimum. So in finding the Higgs boson in 2012 and measuring its mass, we only measured the curvature of the Higgs potential in the immediate vicinity of the current vacuum expectation value of the scalar Higgs field. As such, we know our vacuum must currently sit at a minimum of the Higgs potential, as that's where systems naturally roll. And we know from measuring the Higgs mass that that potential is roughly parabolic around the vacuum expectation value. But that's pretty much all we do know. We know very little about how the vacuum energy of the Higgs field would change if we dialed the Higgs field up to extremely high values, or gradually shut it off. We cannot control the Higgs field strength of the universal vacuum. We are stuck at one field value, one point in time, and one field strength. This should raise alarm bells. Many different shapes of the Higgs potential could reproduce the myopic view we have of the Higgs potential around the vacuum expectation value. All these shapes would allow our vacuum to roll down a potential hill and power up the scalar Higgs field of our modern universe, producing the field that fundamental fermions bounce off to obtain their mass. All these potentials would have resulted in rings of identical vacuum ground states into which the vacuum of our early universe could have rolled, facilitating the spontaneous symmetry breaking of the Higgs field, the production of Goldstone bosons, and the realization of the massive W and Z bosons. Some look very similar to the standard model Higgs potential, but some are radically different. All are the results of physics hypotheses beyond the standard model that could entirely reproduce the experimental behaviour of the Higgs we have observed since 2012, and each is associated with a radically different evolution of our universe. As such, we have to ask a difficult question. Is the standard model Higgs potential really the Higgs potential of our universe? Currently, we simply do not know. Higgs and others ripped the form of the Higgs potential straight out of Landau's theories of ferromagnetic phase transitions, and chose a form of the Higgs field such that it did the job of giving masses to the W and Z bosons, while leaving one Higgs field component switched on throughout the entire universe to provide mass to the fundamental fermions. As such, the Higgs potential is simply put in by hand. It is the simplest and crudest guess regarding the fields permeating our universe that gets the job done. It is a simple model of a ferromagnet slapped onto the evolution of our entire universe. That doesn't mean it is necessarily correct, and it would be phenomenally serendipitous if it were. If the history of particle physics has taught us any lesson, it's that nature rarely seems to implement the simplest solution. A basic example being the fact that the standard model has 3 generations of fundamental fermions. To channel Isidore Rabi, who ordered those? Given the lessons of history, it would be foolish to assume that the standard model Higgs potential nailed the problem on the first attempt, and that we precisely understand the path down which our universe rolled to reach its current position. We need to check. We need to map the Higgs potential. In part 1, we've introduced the scalar Higgs potential and noted how its form is a key prediction of the standard model and solves many problems in fundamental physics. We've also seen that our first measurements of the properties of the Higgs boson, the herald of the scalar Higgs field, tell us very little about the shape of the scalar Higgs potential. Now, I have set the table. Next time, we will discuss why mapping that potential is so incredibly important, and why truly understanding its form and evolution will require the building of larger, more powerful, and more intense particle colliders. It really is an amazing tale. See you next time. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comments section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.